Hi, welcome back to A Slice of Physics. We've talked about motion, forces, momentum, we've talked about linear and circular scenarios, and now we're going to switch gears and talk about energy. We'll discuss what energy is, what types there are, and how we define a system when we talk about energy. Energy is one of those concepts which again is easier to understand than it is to describe. You probably know what it is, and for our course, it'll suffice to think of it as the capacity or ability to do work. And if you're wondering what work is, well, you'll have to wait for the next video to talk about that concept. But we can think of practical examples. When we have a car that speeds up from rest, it's using the fuel to turn into kinetic energy. When you have a baseball player sliding to the base, he's losing kinetic energy, and that's going into heating up the ground under him and the air around him. And so let's begin with the discussion of the types of energy we have. At a high level, I can say that there are four kinds of energy. There's mechanical energy, there's thermal energy, chemical energy, and nuclear energy. We'll spend a lot of our time with mechanical energy, which is why I've reserved a lot of room for it. And mechanical energy comes in two basic types. You've got kinetic energy, which has to do with the energy related to motion. And you have potential energy, which has to do with the state or position an object is in. And when we drill down into kinetic energy, there are two kinds again. There is translational kinetic energy and rotational kinetic energy. And by the way, kinetic energy is written as the letter K. And since we'll be dealing with translational kinetic energy for the most part, we will call that also K. And when we mean rotational kinetic energy, we will call that K subscript rotation, or ROT. The translational kinetic energy depends on the mass of an object and its speed. So its equation is that it's 1/2 times m times v squared. Here v is the speed. Energy is a scalar, so we don't need the vector velocity, we just need the speed. And so let's see what its units might be. The unit of mass is kilogram, the unit of speed is meters per second, and I got to square that because speed is squared over there. So this gives me kilogram meters squared per second squared. And that's the SI unit of energy. Now I can write this in a couple of different ways. We know that kilogram meter per second squared is nothing but Newton, so I can write this as Newton meter. And finally, the name this is given is joules. So the standard international unit of energy is joules, which is the same as Newton meter or kilogram meter squared per second squared. You might know of other units of energy like calories, and we'll talk about a conversion factor between joules and calories later. Rotational kinetic energy is energy that something contains because it is spinning around an axis. And like we've done before, the analogies do work. If you remember, the rotational equivalent of mass is moment of inertia. The rotational equivalent of speed is angular speed. So the rotational kinetic energy is 1/2 I times omega squared. And I'll leave it as an exercise for you to verify that the units for this also come out to be joules like we showed here. Let's take a closer look at translational kinetic energy. So what this tells us is that it depends on the mass and the square of the speed. So if I have a car of mass mc and it's going at a speed of, let's say, 5 miles per hour, it has some kinetic energy. When it's just sitting there, it has zero kinetic energy. But when it's going at 5 miles per hour, it has some kinetic energy. And let's say after a little while, this car speeds up and starts going at 50 miles per hour. It's 10 times the speed. Its kinetic energy will not just be 10 times because v is squared over here. So I got to square that factor. So the kinetic energy will grow to be 100 times what it was at 5 miles per hour. So the kinetic energy is very sensitive to speed. Secondly, because it also depends on mass, if I have a large truck over here and it's got a mass of mt that, let's say, is 7 times the mass of the car, when it's going at the same speed as the car, it'll have a kinetic energy that's 7 times the kinetic energy of the car. Since mass is just a straight factor in this equation, 7 times mass would translate to 7 times kinetic energy. Okay, moving on to potential energy. That's the energy that's related to the position or state of an object. The potential energy that relates to position is called gravitational potential energy. An object can only have potential energy when it is close to another mass, because the gravitational force between two masses is what's responsible for potential energy. Potential energy is written as capital letter U, and so gravitational potential energy could be written as U sub G, and U sub G is the weight of an object, m times g, times the height above a reference point where you set the potential energy to 0. So the other thing about potential energy is that you can set the 0 of potential energy anywhere you want. Just like in a coordinate system, you could set the origin anywhere you want, and then you measure everything with respect to that. So if I have the ground here, and I have a ball that's here at this height, h1, versus another ball that's over here at height h2, that's a bigger height. The second ball, let me number these, ball 2 will have a higher potential energy than ball 1. Higher you are off the ground, the more potential energy you will have. And also, like we discussed before, it is dependent on mass as well. So if I have an object that's a lot more massive at the same height as a lower mass object, in this case object 3, would have a higher potential energy. And once again, I'd like for you to go through the units here and see that you will get joules again. The other kind of potential energy we have that relates to the state of the object is called elastic potential energy or spring potential energy. And we'll write that as U sub S. And we discussed springs a while back. The energy that's associated with a spring is 1/2 kx squared, where k is the stiffness constant of the spring that we discussed that was measured in Newton per meter, and x is the displacement from the equilibrium position. So if I have a spring over here that's in its equilibrium position and being happy, it does not have any elastic potential energy. But now if I stretch the spring and make it bigger by an amount of x, or if I compress the spring and make it smaller by an amount of x, in those cases it would have this potential energy of 1/2 k times x squared. Now let me also briefly discuss the other kinds of energy that exist in a system. Thermal energy is the energy that's associated with the microscopic particles in matter. It's the aggregate of microscopic energies that's contained in molecules and atoms. You probably know that molecules and atoms in substances are not sitting still. They're jiggling, rotating, and moving around all the time, and in gases they are flying around. So they have kinetic energy, and because they have bonds between atoms and molecules, sometimes those bonds are stretched and compressed, so they'll have potential energy, elastic potential energy. And the aggregate of all of those microscopic motions in any contribute to its thermal energy. And it relates to the temperature of an object. A hotter object will have a higher thermal energy than a cooler object. Chemical energy is related to chemical reactions. So when atoms are bound in molecules, there's energy that's associated with their binding, and you can have chemical reactions that change those bonds. And as that is done, the chemical energy is released. And so chemical energy is the energy of bonds in molecules. And finally, we'll talk about nuclear energy, which has to do with the binding of protons and neutrons in a nucleus. And when you change those bonds, you end up releasing an enormous amount of nuclear energy. And by the way, we will call these ETH for thermal energy, EChem for chemical energy, and E-nuclear for nuclear energy. Okay, let me also quickly introduce the concept of a system. A system is an object or a collection of objects for which we want to talk about the energy. So if I have this car over here, and if my system is just the car, it has kinetic energy because it's moving. It has chemical energy because it's got fuel that has chemical energy stored that it can use. And so the total energy of this system would be the sum of the different kinds of energies. In general, the total energy of a system is the sum of its kinetic energy, which could be made up of rotational and translational, plus its potential energy, which could be gravitational and spring, plus its thermal energy, plus its chemical energy, plus nuclear, and so on. So total energy is the sum of all the individual energies. And if I define the system as just the car, it cannot have any potential energy. Remember, I said that potential energy is because of the gravitational interaction between two masses. So you need at least two objects to be defined as the system in order to discuss its potential energy. So now if this car is on a bridge, where it climbs up a ramp and gets on a bridge, and I want to talk about its potential energy, let's say we set 0 potential energy at the ground level here. So this car is now at a height h above that, and so it has a potential energy, but technically that potential energy belongs to the car and the earth, because those are the two masses that have this gravitational interaction. So in order to talk about the potential energy here, Ug from gravity, I have to define my system as the car plus the earth. This slice of physics was all about energy. We discussed the various types of energy and also discussed the importance of defining a system when we talk about energy.